right, team, let's get started. All right. Shh. David, Caleb, thank you. All right. As always, I'm going to give you guys the notes, but I'm going to do it in reference to an NCA question so you can kind of see how what you're learning is going to be applied onto the exam. This is stuff that I've taken from 2 exam papers. Something that I haven't covered with you guys when it comes to organic chemistry is that the other reason why it's really tricky is that it doesn't really have set categories of questions. Thermochemistry is really nice because it does have set, like, you expect certain questions to happen in certain orders sort of thing. Thermochemistry is like structure and bonding. So if you remember structure and bonding last year, there was a question on Lewis structures, shapes, and polarity. There was a question on types of solids, and then there was a question on your enthalpy calculations, and it always had that 3 pattern.
Break 1 courses start making their way to the gym now, please. That's all the Tommy Group students performing at break 1 to the gym, please.
All right. So that's something to keep in mind. What was I going to add about that? Trying to think. So thermal chemistry is going to be very similar like that. It's going to have set categories of questions. Organic is tricky because organic, the material intertwines together, as you guys can see with the flow of the reaction scheme questions. So organic doesn't have set themed questions. It kind of has a list of potential questions, and then they mix and match it. So different years, they have different kind of focuses. You can still expect certain things that are going to happen, like a reaction scheme question, an identification question is going to happen, those sort of stuff. So that's why I had to take 2 different exams to make this question up, because I wanted to give you guys variety in the way they ask the Esther question. With the Esther question, it also ties into other questions as well. So again, this is what I'm saying about the mix match of material. So first thing we have from the 2023 exam from last year is just the naming. There was a section on naming and drawing, but I've only taken the Esther-based question to make sure that you guys know how to name and draw your esters. So remember, when we're looking at this, we're looking to see where the carbonyl is, because that is going to be an indicator of where the molecule cuts. So we're looking for the carbonyl, and we're looking for the single bond oxygen, and that's where the molecule is going to cut in half. That tells me then which is the carboxylic acid component and which is the alcohol component. This here, since it has the carbonyl, is the carboxylic acid component. This here with the single bond and oxygen is the alcohol component. Now, the reason why it's important to note each one is because that's going to influence the naming. So in this case, the alcohol component will go first. I see there's 2 carbons here. So this tells me that the naming is going to be ethyl. And then I look at this carboxylic acid, and that's going to be the O8 ending. Be really, really careful. A lot of people forget to count that carbon for some reason because they just miss it. So it's 1, 2, 3 carbons there. So that would be ethyl propanoate. Are we okay with that? Cool. Okay. Next thing we got to think about is these things called triglycerides. Triglycerides are esters. They're just esters. They're just molecules with 3 ester groups. So just be mindful that triglycerides will pair into the esters. These are just esters, molecules with 3 esters. So that's why I'm including that in today's notes. You'll see here again that there is, like I said, an ester component. See it? Okay. The other thing to keep in mind is the word tri, because that gives us indications of what's going on with how this molecule is designed. So tri, we know, also again means 3, which makes sense because we see 3 esters. The way we form these triglycerides, again, if we look to see where the ester component is, which is right here, you again look for the carbonyl, you look for the single bond and oxygen, and this is where it's going to cut. All right. When it cuts, there are 2 products being formed because I can tell that these 3 are all the same carbon chain, so it's the same carboxylic acid. If they had different chains, then you would just have more products, more carboxylic acids. This guy here is actually a triol. It's got 3 alcohol components. So if I was to draw that one, it would be CH2, CH, CH2, and each carbon has an OH. So remember, it is an alcohol and a carboxylic acid that makes that up. So all I've done is I've cut it right here, and I've just added a hydrogen, like that. So that's a triol, a molecule with 3 alcohols. And then each one of these alcohols can add the carboxylic acid. Are we okay with that? All right, when I break it up over on this side then, I have my carboxylic acids. When I look at the tail, I see that they all have the same length because they're all 16, so I only have one carboxylic acid that's being formed. If these tails were different, then I would have multiple carboxylic acids being formed. So just be mindful when you're looking at that. Now this is in base hydrolysis, so now we're starting to look at how we break apart these organic molecules. So hydrolysis is using water to break apart the molecule, and this is in basic conditions. It's important that we note that it's in basic conditions because what that tells me is that the carboxylic acid is going to be neutralized. So for example, a base that we could use is sodium hydroxide. And when I use that sodium hydroxide, the sodium component is going to attach to my carboxylic acid to neutralize it. So what I would have molecule-wise is, and you can draw it either direction. I would just like to draw it with my carboxylic acids on my right. So CH3, CH2, 16, and then C double bond O. It does get the O back because it's making the carboxylic acid, but it's been neutralized by the base, so that's how we would write that molecule. So I'm just trying to show the neutralization of the carboxylic acid. If this was in acidic conditions, then I wouldn't have the Na, I would just have it as the OH, as a normal carboxylic acid. But because it's in basic conditions, I have to neutralize the carboxylic acid. So that is a very kind of standard triglyceride question. They can ask you to break it, and they can ask you to make it. So be mindful that you have to be able to do this question in both directions. Are we okay with that? I'm just looking at faces to see if people are okay. Cadence is looking okay. Melania, are we okay? All right. How are my boys at that table? Questions? You okay? Okay? All right. That's why I want you guys to look at these Esther questions and do that pre-learning. Okay. So the good news is it's a lot of material, but it's all tied back into Esters at the end of the day. Now you can see some of the things we were talking about in that previous lesson, and this is what I mean by the integration of organic material, and that's how the questions can kind of chop and change. In this case, they want you to select the following bit of equipment used to hydrolyze the triglyceride and give reasons for your choice. So they've given a distillation, they've given a reflux, and they've given a separation technique as well. So which one do you think you would need to do to make the triglyceride hydrolyze? Reflux. Why reflux? Yes. It traps it and ensures 100% reaction. So I don't want to use distillation because there's nothing that I'm trying to purify and get rid of or prevent from reacting. So B is the correct answer. I'm not going to write down the reasonings. I think you guys are okay with that. It's just to basically ensure 100% of the reaction occurs. Are we good? All right, backside. Cool. All right, now this is where it gets tricky. So that's why I want to show you this sort of stuff. All right, so we talked about esters. We talked about triglycerides, which is a type of ester. It has 3 components or 3 ester bits to it. The last thing that we need to talk about is polyesters. So polymers means repeating units. So plastics are a really good example of a polymer. It's a repeated unit, and depending on what you have in that chemical formula for that polymer, you get different types of plastic. So for example, the chairs that we're sitting on is a hard plastic, whereas the wire that's connecting my document camera is a soft plastic. These are going to have different polymer formulas in order to make it have its certain properties. This is an example of one, which is a polyester. So it just means that we have a repeating unit, and that repeating unit has an ester bridge to make it connect together. There's lots of different polymers. We'll also talk about polyamides. We'll also talk about, what's the other one? Addition polymers. Addition polymers is something that was covered in level 2. It's unlikely to come up again than in level 3 because the focus is these condensation polymers. So what we're looking at here is a repeating unit. There are two different ways we can make a polyester. Either I have a molecule that has both the alcohol and the carboxylic acid component, so that way I can join it together to make an ester, or I have two molecules, one that is a dicarboxylic acid and one that is a diol. So what I need basically for a polymer to form is I need to have both ends of the molecule being able to attach in an ester form. Are you okay with that? Or do you want me to write that down? Write it down? Okay. So when I want to make a polyester, I have two choices. So in order to make a polyester, so a repeating unit, a repeated structure that has esters as the link, I have two ways to do it. The first way I can do it is I can have one molecule that has an alcohol and a carboxylic acid. That's one way I can do it. The reason why I need both is so that way they connect together. It's a branch. The second way I can do it is I have two molecules. One that's a diol, which means it has two alcohol components, and one that's a dicarboxylic acid. So it has two carboxylic acids, one on each end of the molecule. So there's the two ways I can make it. They can give you either one on the assessment, so you do need to know how to recognize both. So they've given me polyethylene I can't even read that, the PET is the acronym for it. It's a polyester used to create fibers, film, and packaging. They've shown the repeating unit. So when we're doing polyesters, the way we communicate that across is we do these square brackets, and what we're saying is this is what the repeating chain looks like. They can often ask you to draw a polymer and showing its repeated chain, and they often would want you to draw probably two repeats just so you know what the pattern is. If you just draw it once, then you're like, do you really know what you're doing? If you're doing it twice, then you actually know. All right, so they want you to circle one ester functional group because there's lots of esters there. So again, we're looking for the carbonyl and we're looking for that single bonded oxygen, and that here is my ester. And what we'll notice in this polyester is that the way the polyester is joined together is by lots of ester linkages, because we know that when we make an ester, we put two molecules together. So they want you to do the hydrolysis of this in both acidic and basic conditions. They want you to explain what hydrolysis is. They want you to talk about the reagents and conditions you'll need. And they'll also want to note the products of the acid and the base hydrolysis in the boxes provided. So that's everything that they're looking for. Just as a reminder of what some of this terminology means, hydro means water. And lysis, just like when you guys think about biology and you cell lysis, it means to break apart. So when I combine those two words together, I'm talking about breaking apart molecules with water. When it comes to acidic and basic conditions, it just basically, you're looking at reagents like sodium hydroxide or, what's another one? Hydrochloric acid, those sort of things. You're just basically looking at it mixed in water, so that way it helps break it apart. So that is a pretty bulk standard thing that you need. Heat will probably help as well. The main thing that people struggle with is how to break them apart in acidic versus basic conditions. So when we look at this molecule here, it is going to break, again, where that carbon and that single bonded oxygen is, and it's going to break each time that you see that. What you should hopefully be able to see are the two molecules that are forming. You have this molecule here, which is your dicarboxylic acid, and this molecule here, which is your diol. And then you go back to the carboxylic acid, and then back to the diol. And so that is my repeating unit. So in this case, when I look at this molecule here, I have option number 2. We have two different molecules that are building up this polymer. In acidic conditions, actually, let me backtrack. In both conditions, whether it's acidic or basic, you're going to get the same alcohol because the alcohol is not affected by the pH conditions. So in both answers, you can write down the alcohol. In this case, it's 2 carbons in length with an oxygen at the end. So I know it must be CH2, CH2, let me pull that down, OH, and OH like that. So that is FN12-diol if I was going to name it. Are we okay with that? All right. Again, in basic conditions, doesn't matter because the alcohol is not going to be affected by it. You still have the same molecule, like that. Cool. The one that's going to be tricky is going to be the carboxylic acid, because the carboxylic acid can get neutralized in a base. So when we're talking about that carboxylic acid in the basic solution, be mindful they have given this to you, and this is just a benzene ring. Don't freak out if you see that. It's just draw that same structure, and you're fine. So I'm going to have this guy here. You can draw it as a circle, or you can draw it as alternating dashes like that. Both of them are communicating the same thing. Then I have a carbon coming off of each, and then I have a carboxylic acid component. So that's C double bond O, C double bond O, OH, OH. So that's in acidic conditions. So you see how this guy has bonded together. It's taken off the OH, it's taken off the H, and that's how the link is formed for that polyester. The only thing that you change in basic conditions then is you just draw the same molecule, you move the hydrogens, and you just neutralize it. That's it. Let's again assume I've used sodium hydroxide. So it will be neutralized with the sodium. That's it. Not too bad, I hope. All right, I'll pull up the marking schedule just to show you guys how the points broke down. Obviously, I haven't written it in a full, nice way. I'm just kind of doing a bridge so you guys have the notes. All right, questions so far before I move it? No? We're just breaking and making our esters, that's all. Just different fancy versions of esters. All right, can I move it? Yep. Okay, so let me just pull up the marking schedule so you guys can see how the points broke down. Again, I'm hoping you guys kind of realize what I've been saying over and over and again, that the organic chemistry is not too bad for getting excellence. You'll see how the points break down, hopefully, if my internet decides to work. Let me try changing my internet. It's been doing this a lot lately, and it's been really irritating. It's like, I'm in the middle of teaching, and I want to be able to access my resources. Are you going to let me do that? No, because you're being a pain in the butt. Usually the only way to fix this is to restart my computer. I'm just going to pause the recording. Okay. Cool. Let me just pull up the marking schedule so you guys can see how the points broke down. Okay, this one that we first looked at, the 2023, there we go. Question 3. Just want to show you guys what that marking points broke down. Ooh. Okay. Ooh, too much. Okay. Question A. Did I swap these around? Oh, this is the 2021 one. Let me get the 2023 one. First one I'm looking at. We'll close that. Oh, it's already done. Let's make this a bit bigger. Okay. So here are how the points broke down, just so you guys know. This is question 3. That's question 2. All right. Question 3, I just took the naming, so you can see that ethyl propanoate is correct from what I've written down. Just be mindful, the question, I didn't include everything, but it had 1, 2, 3, 4 molecules to name, and it was 3 out of 4 for the achieved. It usually isn't a big point, that one. Cool. This one here, you can see triglyceride, we broke it apart. Oh, just be mindful, I did not balance my equation. You're going to need 3 sodium hydroxides for that because there are 3 carboxylic acids, and that was the other thing that I made a mistake on there. It should be a 3 in both of those because I didn't realize it was a balanced equation. That was my bad. All right. And then the other thing they were looking for is B, and an explanation. Heating under refluxes increases the rate of reaction without loss of any volatile reactants and products, ensures the reaction goes to completion. So this one here, Adding a strong base is an achieved point or one correct product. So either you figured out that there's going to be a triol, or you figured out the carboxylic acid salt. The other thing is select B with one valid reason. So those were the achieved points there. The merit was the correct structural formula for both products. How crazy easy is that? So if you had gotten this and this written down correctly, merit point. Select B with two valid reasons. So when you're explaining it, it's not just, oh, I want to have a high yield. It's also, I want to make sure I don't lose anything in that process. And then this one, balanced equation with correct structural formula, and indicates aqueous solutions. So I would have gotten a merit point instead of an excellence point because I forgot to balance it. I think that's a really... And I forgot to write aqueous. It's a really unfair thing to kind of mark you guys on because it doesn't look like an equation. All right. And then the 2021, looking at this question here. Again, achieved is just circling any of these esters. There were 3 that were actually present. The other thing is, for the achieved, describe hydrolysis or provide reagents and conditions. So you need diluted sodium hydroxide or sulfuric acid, and then one correct structural formula product correct. So when I say 1, there's 1, 2, 3, 4. Any one of those would have been an achieve point. Explains hydrolysis, including reagents and structural formula for at least 2 products. So just giving me the definition of it and stating that what you're going to need. So for the acid, I just need some sort of dilute acid, and for the base, I need a dilute base. At least 2 products. It doesn't state which 2 products. So, 1, 2, or 1, 2, or 1, 2, or 1, 2. That's a merit point. How crazy simple is that? The excellence is elaborating on the acid-base hydrolysis of PETs, including all structural formula and product. The main thing I would say here is that they are both forming the same alcohol. The only difference is you're going to have one with a neutralized carboxylic acid. Also, the other note of detail is that you need to specify that this carbonyl is getting the OH from the water, and the CO is getting the hydrogen from the water. So just be mindful that you actually give me specifics. That was an excellence point. So obviously I'm not going to get it because I didn't write the justification here, but I'm hoping you guys are realizing that once you have the basics of organic, it's actually not that hard. It is ridiculous what they're willing to give points for. Like, seriously. Cadence is looking like, yeah, I made the right choice. It was worth sticking it out. It is. It is. Yeah. Alrighty.